Right now, there are structures on the ocean floor that science cannot explain. Not anomalies too small to measure or too vague to photograph. Massive, geometric formations sitting in shallow water off populated coastlines, documented by professional geologists, dived by researchers for decades, and still without a definitive answer. The ocean covers 71% of this planet. We have explored less than 5% of it. What we have found in that 5% already does not fit the story we thought we knew. What the other 95% is holding, we have no idea. If you enjoy drifting into the deep ocean and discovering what lies beneath, please consider liking and subscribing. It truly helps more than you know. Are you ready? Let's begin. In 1987, a diving instructor named Kihachiro Aratake was looking for hammerhead sharks off the southern tip of Yonaguni Island in Japan. He did not find the sharks. What he found instead was a structure on the ocean floor at a depth of 27 meters that stopped him completely. There were steps, not suggestions of steps, not geological formations that vaguely resembled steps if you tilted your head and imagined. Flat, horizontal surfaces separated by clean vertical faces, stacked one above the other in a progression that ascended toward the surface like the terraced side of a pyramid. Aratake surfaced, went back to shore, and told people what he had seen. Nobody believed him until they went down and looked for themselves. What they found has been argued about ever since, and the argument has not been resolved because the structure at Yonaguni does not fit cleanly into any category that science has a comfortable answer for. It is either the most remarkable example of natural rock formation ever documented, shaped entirely by geological processes without any human involvement, or it is the remains of something built by people who should not have been capable of building it at the time the ocean covered it. There is no third option, and neither of the two available options is easy to accept. The Yonaguni Monument, as it came to be called, covers an area of roughly 60 by 150 meters on the seafloor. It rises approximately 27 meters from its base to its highest point. The main feature that draws the eye immediately, and that has driven the debate for decades, is the terrace structure, a series of flat platforms separated by near vertical walls, the largest terrace, measuring roughly 20 meters wide and 100 meters long, with walls that rise up to 8 meters. This is not a small anomaly at the edge of a reef. This is a massive, organized structure sitting on the seafloor off a populated island, visible to any diver willing to descend to recreational diving depth, and it has two competing explanations that the scientific community has not been able to decide between in nearly 40 years of investigation. The geological argument goes like this. Yonaguni Island is composed of a fine-grained mudstone and sandstone called Ryukyu limestone, a sedimentary rock that tends to fracture along horizontal and vertical planes when it is subjected to the stress of tectonic activity. The island sits in a seismically active region. Earthquakes are common. When sedimentary rock fractures along its natural planes of weakness, it can produce flat surfaces, right angles, and regular geometric forms without any tool ever touching it. The terraced appearance of the monument could be the result of centuries of wave action, current erosion, and seismic fracturing acting on a rock that was predisposed by its internal structure to break in regular ways. Under this interpretation, what Aratake found was an unusually dramatic example of natural geological sculpting, impressive and worth studying, but not evidence of anything that challenges existing history. The problem with a geological argument is not that it is wrong. It may be entirely right. The problem is that it does not explain everything. Among the features documented at the Yonaguni site are what appear to be a road or pathway running along the base of the main terrace structure. Two megalithic standing stones positioned upright near the main formation. What appears to be a stone basin or pool with a flat bottom, a triangular depression that some researchers have interpreted as a gateway, and a formation that has been described by the Japanese geologist Masaki Kimura, who has spent more time diving the site than anyone else, as a human face carved in profile from the rock. Kimura spent 15 years diving Yonaguni and cataloged more than 20 features that he argues cannot be explained by natural fracturing alone. His position, contested by other geologists, is that the monument is a man-made structure, or at minimum a natural formation that was modified by human hands, and that it dates to a period between 2,000 and 10,000 years ago, before the last major rise in sea level submerged this part of the Japanese coast. This is where the argument becomes genuinely uncomfortable for mainstream archaeology, because if Kimura is right, the implications are serious. 10,000 years ago, the area around Yonaguni was above water. The sea level rise that followed the end of the last ice age submerged coastal regions across the world, and the timing is consistent with a structure built on what was then dry land being gradually covered by rising water over millennia. But 10,000 years ago, the cultures present in that part of the world were not supposed to be capable of constructing terraced stone monuments of this scale. The earliest known examples of monumental stone architecture appear in the archaeological record around 5,000 to 6,000 years ago in the Middle East and Egypt. A structure at Yonaguni dating to 10,000 years before the present would predate that by several thousand years, which would require revising not just the timeline of Japanese prehistory, but the timeline of human architectural development globally. This is why geologists who are not committed to the natural formation explanation are cautious. The stakes of being wrong in either direction are high. Robert Schoch, the Boston University geologist who became known for arguing that the Sphinx at Giza was older than mainstream Egyptology, accepted based on weathering patterns, has dived Yonaguni and concluded that it is primarily a natural formation. Schoch's position is that the regular geometry is real, but explicable by the rock's fracture patterns, and that there is no convincing evidence of tooling or human modification. Kimura's position is that the regularity and the combination of features exceed what natural processes can account for. Both men are professional geologists who have examined the same site. They disagree. That disagreement has not narrowed over time. It has persisted because the evidence is genuinely ambiguous and because the site is underwater, which makes the kind of detailed, systematic excavation that would settle the question on land extremely difficult and expensive to conduct on the seafloor. What is not ambiguous is what the seafloor looks like in the area around Yonaguni beyond the main monument. The wider seabed in the region contains additional formations, some of which share the geometric regularity of the monument, and some of which are clearly natural rock. The difficulty of distinguishing the artificial from the natural when both are submerged, eroded by decades of current and biological growth, and accessible only to divers with limited bottom time, is not a failure of scientific method. It is a genuine epistemological problem. The ocean does not make investigation easy. It imposes conditions that would make any archaeological site difficult to read, and it has been working on Yonaguni for somewhere between 2,000 and 10,000 years, depending on which side of the argument you find more convincing. The sea level history that created the conditions for this mystery is itself a record of change on a scale that the human mind struggles to hold. At the peak of the last glacial maximum, approximately 20,000 years ago, global sea levels were roughly 120 meters lower than they are today. The water that now covers the continental shelves, the shallow coastal seas, the straits between islands, was locked up in ice sheets covering large portions of North America, Europe, and Asia. Coastal regions that are now underwater were dry land. Rivers that now discharge into the sea ran across exposed continental shelves before reaching the ocean. The geography of the world's coastlines was fundamentally different, and the areas where human populations lived and built structures were in many cases in regions that are now submerged. The archaeological record of coastal civilizations from this period is almost entirely lost because the sites where those people lived are now underwater. Yonaguni sits in this gap, in the space between what we know happened and what the ocean has covered, and it refuses to resolve itself into a clean answer. 8,000 kilometers to the east of Yonaguni, in the shallow waters off the coast of North Bimini in the Bahamas, there is another structure on the seafloor that has generated a comparable argument for a comparable length of time. The Bimini Road, discovered by divers in 1968, consists of a linear arrangement of large, flat limestone blocks stretching for approximately 800 meters along the seafloor at a depth of 5 to 6 meters. The blocks are roughly rectangular, ranging from about 1 to 4 meters across, and they are arranged in what appears to be a double row with a consistent orientation. The formation looks, to any diver who swims along it, like a paved road or causeway that has been on the seafloor long enough to accumulate coral growth and marine sediment on its upper surfaces. The debate over the Bimini Road follows the same structure as the Yonaguni debate, with a geological explanation on one side and an archaeological interpretation on the other, and a same fundamental inability to reach consensus after more than 50 years of investigation. The geological argument holds that the blocks are a natural beach rock formation. Beach rock is a sedimentary rock that forms in tropical coastal environments when carbonate sediment is cemented together by calcium carbonate precipitated from seawater. It tends to fracture along the stress lines created by wave action, producing rectangular and polygonal blocks that can look when seen from above or at an angle, like arranged paving stones. The 5 to 6 meter depth at which the Bimini Road sits is consistent with the beach rock formation that was at the shoreline during a period of lower sea level and was gradually submerged as sea levels rose. Under this interpretation, the apparent regularity of the Bimini Road is a consequence of the natural fracture patterns of beach rock, and the double row appearance is a coincidence of how the rock happened to break. The counter-argument focuses on several features of the Bimini Road that proponents of an artificial origin argue are difficult to explain as natural beach rock. The blocks do not simply lie flat on the seafloor. Some of them are supported by smaller stones underneath their corners, a configuration that some researchers argue is inconsistent with natural formation and suggests deliberate placement to level the blocks. The double row structure, if genuine, would require an explanation for why two parallel lines of beach rock formed with a consistent separation between them. And the overall scale and linearity of the formation exceeds what most documented examples of natural beach rock fracturing produce. The researcher, Manson Valentine, who was one of the original discoverers of the formation in 1968, argued until his death that it was a remnant of a collapsed ancient structure, possibly a harbor wall or causeway associated with a coastal settlement now entirely submerged. The Bimini Road acquired an additional layer of significance because of a prediction made by the American psychic Edgar Cayce in the 1930s, who claimed that evidence of the lost continent of Atlantis would be found near Bimini in 1968 or 69. The discovery of the road in 1968 was seized on by Cayce's followers as confirmation of his prophecy, and the association between the Bimini Road and Atlantis mythology has persisted in popular culture ever since. This association has been damaging to serious scientific investigation of the site because it has made it easy to dismiss archaeological interest in the formation as fringe speculation, and because it has attracted researchers whose primary motivation is confirming a predetermined conclusion rather than following the evidence. The scientific investigation of the Bimini Road has suffered from being caught between credulous enthusiasts who want it to be Atlantis and skeptical scientists who do not want to be associated with Atlantis mythology. Neither position serves the actual question, which is simply whether the formation is natural or artificial, and which has not been conclusively answered. What connects Yonaguni and Bimini, beyond the surface similarity of their geometric regularity and the contested nature of their origin, is the broader problem they represent for our understanding of the prehistoric coastal world. Both sites are in regions that were above sea level during periods when human populations were present. Both have features that some qualified researchers argue cannot be fully explained by natural geological processes, and both are in locations where the conditions for systematic archaeological investigation are genuinely difficult. Underwater archaeology is expensive, technically demanding, and limited in the time investigators can spend examining any given area. The tools and methods that have resolved comparable debates on land, detailed stratigraphy, systematic excavation, carbon dating of organic material in direct association with structural features, are harder to apply underwater and in some cases impossible. The ocean has covered a significant portion of the habitable coastal world that existed during the glacial maximum and the following period of sea level rise. The coastlines where human populations lived during those periods, the areas most likely to have been densely inhabited because coastal environments offer access to marine food resources, terrestrial game, and fresh water simultaneously, are now underwater in most parts of the world. The archaeological record of the period from 20,000 to 8,000 years ago is therefore systematically biased away from coastal sites. And the picture we have of human prehistory during that period is constructed almost entirely from inland sites that happen to remain above the rising sea. What was lost when the coasts went under is a question that underwater archaeology is only beginning to be equipped to ask seriously, and Yonaguni and Bimini are among the clearest examples of why the question matters. The sonar surveys that have been mapping the ocean floor with increasing resolution over the past 3 decades have added a new dimension to this problem. Side-scan sonar and multi-beam echo sounders can produce detailed images of seafloor topography at resolution sufficient to identify features of the scale of the Yonaguni monument or the Bimini Road from a surface vessel, without requiring divers. These surveys have been conducted across large areas of the continental shelves in various parts of the world, and they have returned results that are not always easy to explain. Regular geometric formations on the seafloor of the North Sea, which was dry land during the glacial maximum and was inhabited by people whose descendants are the ancestors of modern northern Europeans. Anomalous linear features on the shelf off the coast of India that some researchers have argued are consistent with ancient habitation. Formations on the floor of the Black Sea, which was a freshwater lake rather than a sea during the last ice age, and was transformed by a sudden and catastrophic inflow of salt water from the Mediterranean approximately 7,500 years ago, an event that some researchers have linked to the widespread flood narratives found in cultures from the Middle East to South Asia. The Black Sea connection is worth examining carefully because it has better evidence behind it than most of the other anomalous seafloor findings. In the late 1990s, the oceanographers William Ryan and Walter Pittman at Columbia University published evidence from sediment cores and sonar surveys suggesting that the Black Sea was indeed a freshwater basin until approximately 7,500 years ago, when the rising Mediterranean broke through the natural land barrier at what is now the Bosphorus Strait and flooded the Black Sea basin in what may have been a catastrophic event. Subsequent surveys by Robert Ballard, the oceanographer who located the Titanic, found evidence of ancient shorelines on the Black Sea floor at depths consistent with a pre-flood basin level, and in 2000 found what appeared to be wooden structural remains on the Black Sea floor, in water deep enough that the absence of oxygen, which characterizes the deep Black Sea, would have preserved organic material indefinitely. The Black Sea findings are more securely grounded in documented geology and oceanography than Yonaguni or Bimini. The flood event is real. The ancient shorelines are real. Whether the structural remains Ballard identified are genuinely anthropogenic and whether they are connected to the flood event is less certain, but the questions are legitimate and the setting for answering them, an enclosed sea with anoxic deep water that preserves organic material is uniquely favorable compared to the open ocean environments where Yonaguni and Bimini sit. The structures are one thing, but the ocean does not only hide what humans left behind, it hides what was never human at all. The giant squid existed in the scientific literature for over a century before anyone saw one alive. Not in captivity, not in the wild, not on video, not even a clear photograph. For 150 years, everything science knew about Architeuthis ducks came from dead animals. Carcasses washed up on beaches, partial remains recovered from the stomachs of sperm whales, fragments of tentacle hauled up in deep-sea trawls alongside other things that did not survive the journey to the surface. The animal itself, alive, moving, behaving, existing in the environment it actually lived in, was completely unknown. Researchers estimated its size from the fragments. They inferred its behavior from the wounds on sperm whales that hunted it. They constructed a picture of an animal from the pieces of animals that were already dead. And that picture, assembled from carcasses and inference over 150 years, turned out to be wrong in ways that nobody expected. The first confirmed photograph of a living giant squid in its natural habitat was taken in 2004 by Japanese researchers Tsunemi Kubodera and Kyoichi Mori. They had deployed a camera on a long line at a depth of 900 meters in the North Pacific, baited with a smaller squid, and they waited. What the camera eventually captured was not what the prevailing model of the giant squid predicted. The animal in the photographs was not sluggish. It was not the passive, drifting predator that had been inferred from the deep-sea environment it occupied. It attacked the bait aggressively, became entangled in the line, and then severed its own tentacle to free itself and escape. The photographs showed an animal that was active, fast, and capable of decisive action under pressure. In 2006, Kubodera's team obtained video footage of a living giant squid at the surface, brought up from depth by the entanglement. It was the first time any living individual of the species had been seen by human eyes in anything other than a dying state. In 2012, a team, including Kubodera and the filmmaker Fyodor Pitcairn, captured the first footage of a giant squid in its natural deep-sea habitat, filmed by a specially designed low-light camera system that produced no white light, using only red light that the squid's photoreceptors are largely insensitive to. The animal on that footage was nothing like the pale, inert carcasses in museum collections. It was iridescent. It moved with a fluid, purposeful grace. It was, in the word used by one of the researchers watching the footage for the first time, magnificent. What the giant squid story illustrates is not simply that a large animal can remain unobserved for a long time. It illustrates the scale of the epistemological gap between what the deep ocean contains and what science has been able to directly observe. The giant squid reaches lengths of up to 13 meters, including tentacles, making it one of the largest invertebrates on Earth. It has the largest eyes of any living animal, up to 30 centimeters in diameter, eyes that evolved to detect the bioluminescent flashes produced by sperm whales hunting at depth in near-total darkness. It is a major prey item for sperm whales globally, which means it exists in sufficient numbers to sustain the populations of one of the largest predators in the ocean. And yet, it was not seen alive in its natural environment until 2004. If an animal of this size and ecological significance can remain visually unobserved for the entire history of deep-sea biology, the question of what else is down there. In the 95% of the ocean that has never been directly imaged, is not a rhetorical question. It is a genuine statement of ignorance. The colossal squid, Mesonychoteuthis hamiltoni, is larger than the giant squid by mass, though not necessarily by length, and it is even less known. The first complete adult specimen was not recovered until 2007, when a New Zealand fishing vessel operating in the Ross Sea in Antarctica hauled one up from a depth of approximately 1,000 meters. The animal weighed 495 kilograms. It was approximately 10 meters long. Its eyes, examined after the specimen was frozen and later thawed for scientific study, were 27 centimeters in diameter, the largest eyes ever measured in an animal. Almost nothing is known about the colossal squid's behavior, its reproductive biology, its population size, or its precise depth range. The 2007 specimen remains the most complete adult colossal squid ever examined. Everything else known about the species comes from fragments recovered from whale stomachs and a small number of partial specimens. An animal that may be the largest invertebrate on Earth by mass is known almost entirely from one dead individual and pieces of others. The deep ocean is not withholding minor curiosities. It is withholding the basic facts about some of the largest animals alive. The deep scattering layer, the dense aggregation of organisms that occupies the mesopelagic zone between approximately 200 and 1,000 meters depth, is one of the most biomass-rich environments on Earth, and one of the least understood. It was first detected during World War II by Navy sonar operators who noticed that their echo sounders were returning signals from a layer at intermediate depths that appeared to rise toward the surface at night and descend during the passes day. They initially interpreted it as a false bottom, a phantom seafloor that moved. It was eventually understood to be a massive aggregation of living organisms, primarily fish, squid, and crustaceans, performing a daily vertical migration of hundreds of meters in response to light levels. At night, they rise toward the surface to feed on the plankton-rich surface waters. During the day, they descend back into the darkness to avoid visual predators. This migration, performed every day by organisms numbering in the trillions across the world's oceans, represents one of the largest coordinated animal movements on the planet. And despite being known about for 80 years, the biological composition of the deep scattering layer is still not fully characterized. The nets used to sample it are not fine enough to capture the smallest organisms. The trawls used to collect larger organisms disturb the layer and produce samples that do not accurately represent its natural composition. Remote sensing can measure the layer's depth and density, but cannot identify what species it contains at a given location. The deep scattering layer is everywhere in the ocean. It contains an enormous fraction of the ocean's total biological productivity, and science does not have a complete inventory of what is in it. The bioluminescence that pervades the deep ocean is produced by an estimated 76% of deep-sea organisms, making it by far the most common form of light production in the ocean's volume. It is used for predation, for defense, for communication and for purposes that are not yet understood. The range of bioluminescent mechanisms, the biochemical pathways, and the structural adaptations that produce light in deep-sea organisms is considerably wider than the range found in terrestrial or shallow water bioluminescent species, suggesting that bioluminescence has evolved independently many times in the deep ocean under the selection pressures of a lightless environment, where the ability to produce light confers advantages that have no terrestrial equivalent. The specific signals that some deep-sea organisms produce, the patterns of flashing, the colors, the timing, appear to carry information beyond simple predator deterrence or prey attraction. Some species produce signals whose function has not been determined. The MBARI Research Institution has documented bioluminescent displays in deep-sea organisms captured on ROV video that do not match any known function and that have prompted researchers to describe them simply as unexplained. An organism communicating in a language that science has not yet decoded is not a metaphor. It is a description of what the video shows. The vampire squid, Vampiroteuthis infernalis, whose name means literally the vampire squid from hell, occupies a unique position in cephalopod evolution. It is the sole living member of its own taxonomic order, Vampiromorphida, a lineage that diverged from the ancestors of both squid and octopus approximately 300 million years ago, and has persisted since then as a relict, a living remnant of an ancient evolutionary branch that has no other surviving members. The vampire squid is not actually a squid. It is not an octopus. It is something older than both, a survivor from a time before the modern cephalopod groups had fully separated, carrying in its body plant features that belong to both and to neither. It lives in the oxygen minimum zone, the layer of the ocean at depths of approximately 600 to 900 meters, where oxygen concentration is at its lowest because the decomposition of organic material sinking from above consumes oxygen faster than circulation can replenish it. Most animals cannot survive in the oxygen minimum zone. The vampire squid not only survives there, it thrives. It has the lowest metabolic rate of any cephalopod, allowing it to function on the minimal oxygen available. Its blood contains a form of hemocyanin with an unusually high affinity for oxygen, extracting the maximum possible amount from each unit of water it processes. It has evolved to inhabit the one zone in the ocean that most predators cannot follow it into, a refuge purchased at the cost of living in an environment that would kill almost anything else. The Hadal Zone, the deepest parts of the ocean found in the trenches below 6,000 meters, was long assumed to be essentially lifeless, an environment so extreme in pressure, so cold, so dark, and so isolated that only the simplest organisms could survive there. This assumption was wrong. The Mariana Trench, the deepest point on Earth at approximately 11,000 meters, was found to contain fish when the first detailed biological surveys were conducted. Specifically, it contains snailfish of the family Liparidae, which have been documented at depth exceeding 8,000 meters, making them the deepest living vertebrates known to science. The physiology that allows a fish to survive at pressures exceeding 800 atmospheres pressures that would crush the body of any surface-dwelling fish instantly, involves a set of molecular adaptations that are only now being characterized. The cell membranes of deep-sea fish contain a higher proportion of unsaturated fatty acids, which remain fluid at high pressure, while the cell membranes of surface fish would solidify and cease to function. Their proteins contain stabilizing compounds called piezolites that counteract the pressure-induced denaturation that would destroy the three-dimensional structure of proteins at those depths. The biochemistry of life at the bottom of the Mariana Trench is not simply the biochemistry of surface life scaled for extreme conditions. It is a different biochemistry, one that has been shaped by millions of years of evolution in an environment that does not exist anywhere else on Earth. The discovery of hydrothermal vent ecosystems in 1977 fundamentally changed biology's understanding of the conditions under which life can exist. Before that discovery, all ecosystems on Earth were understood to be ultimately dependent on sunlight, either directly through photosynthesis or indirectly through the food chains that photosynthesis supported. The vent ecosystems are not. They are powered by chemosynthesis, the metabolic process by which certain bacteria and archaea extract energy from the chemical reactions between the hydrogen sulfide and other compounds venting from the seafloor and the cold, oxygenated water of the deep ocean. The communities that have assembled around these vents, tube worms reaching 2 meters in length, ghostly white crabs, mats of microbial life covering the seafloor, clams and mussels with no eyes living in complete darkness, are supported entirely by this chemosynthetic energy source without any dependence on sunlight. This was not predicted, it was not expected, and it has since been documented at cold seeps, at hydrothermal vents across all ocean basins, and in isolated deep-sea environments that have no connection to surface productivity. The possibility space for life was permanently expanded by what was found at those vents, and the expansion has implications that extend far beyond ocean biology. The Mariana snailfish, photographed at 8,336 meters in 2023, set a new depth record for fish. It was filmed by a lander deployed by the University of Western Australia and the Chinese Institute of Deep Sea Science and Engineering. The footage shows a pale, translucent animal moving across the seafloor with what appears to be unhurried confidence in an environment that, by any surface world standard, should be incompatible with complex vertebrate life. The depth record will likely be broken again. The snailfish appeared to be approaching the theoretical limit of vertebrate biochemistry at hadal depths, a limit set not by pressure alone, but by the solubility of trimethylamine oxide, the piezolite that stabilizes their proteins, which become saturated in body tissues at approximately 8,000 to 8,500 meters. Whether evolution has found or will find a biochemical workaround to this limit, some other molecular mechanism that performs the same stabilizing function without the solubility constraint, is an open question. The deepest point of the Mariana Trench is still 2,500 meters below the current depth record for fish. What lives there, if anything lives there, has not been documented. The census of marine life conducted between 2000 and 2010, involving more than 2,700 scientists from 80 countries and costing approximately $650 million, was the most comprehensive effort ever made to inventory the living contents of the ocean. It documented approximately 250,000 known marine species and estimated that the total number of marine species, including those not yet discovered and described, was likely between 700,000 and 1 million. The census was a landmark achievement, and its limitations were clearly stated by its authors. It sampled a fraction of the ocean's volume. It could not effectively sample the deep sea at the resolution required to find small or rare organisms. Its estimates of undiscovered species were necessarily rough. The conclusion that somewhere between half and three-quarters of all marine species remain undescribed by science was not a surprising finding to marine biologists. It was a confirmation of what the pace of new species descriptions had been suggesting for decades. Every deep-sea expedition with the right equipment in the right place finds things that have not been seen before. The rate of new species discovery in the deep ocean has not declined. It has increased as ROV technology has improved and as more expeditions have been conducted in previously unsampled areas. The ocean is not gradually yielding its biological secrets at a rate that suggests we are close to a complete inventory. The rate of discovery suggests the opposite. The more carefully we look, the more there is. The question that the biology of the deep ocean ultimately poses is not simply how many species remain undiscovered. It is what those undiscovered species might reveal about the principles that govern life at the extremes of the physical environment. Every organism adapted to a depth of 8,000 meters. Every creature thriving in the oxygen minimum zone. Every animal generating its own light in permanent darkness carries in its biochemistry and its behavior a set of evolutionary solutions to problems that have no surface equivalent. Those solutions, when they are eventually described and understood, will say something about the range of conditions under which life can organize itself that cannot be learned from any other source. The deep ocean is not merely a place where unknown animals live. It is a laboratory in which evolution has been running experiments for hundreds of millions of years under conditions that do not exist anywhere else. And the results of those experiments, the organisms that have survived them, are still down there in the dark, undiscovered, uncharacterized, doing things that biology has not yet found the language to describe. The xenophyophores, single-celled organisms found on the deep sea floor at depths exceeding 8,000 meters, are the largest individual cells known to exist. A single xenophyophore can reach 20 centimeters in diameter, making it visible to the naked eye as a lacy, branching structure on the seafloor. It is one cell, one nucleus, one set of genetic material, one cellular membrane enclosing a body the size of a human fist. The existence of a single-celled organism of this size violates the intuitions built from familiarity with surface biology, where cells are microscopic and multicellular organization is the prerequisite for visible body size. The xenophyophore achieves its size by incorporating sediment particles into its structure, building a mineral skeleton that supports the otherwise unsupportable volume of cytoplasm. How it feeds, how it reproduces, and why single-celled organization persists at this scale in the deep ocean while multicellular organization dominates everywhere else, are questions that have not been fully answered. The largest individual cell on Earth lives at the bottom of the ocean. Science does not entirely understand it. And if that is what we find when we look at what we have already found, the question of what we have not yet looked at is the one that should keep you awake. The biology of the deep ocean is strange enough. What the ocean does with physics is stranger still. On the night of January 25th, 1995, the crew of the British merchant vessel SS Lima was sailing through the northwestern Indian Ocean when they noticed something wrong with the water around them. It was glowing, not the faint, flickering bioluminescence that sailors sometimes see when waves disturb plankton near the surface. This was different. The entire ocean surface, in every direction as far as they could see, was producing a steady, uniform, milky blue-white light. The ship was surrounded by glowing water. The glow extended to the horizon. It had no edge that the crew could identify. They were not passing through it. They were inside it. And the light showed no sign of stopping. The crew reported the observation. The report was logged. It was filed away alongside hundreds of similar reports that sailors had been making for centuries, reports that were treated by science for most of that time as probable exaggeration, misidentification, or the product of tired eyes at sea in the dark. Then, in 2005, a team of researchers at the Naval Research Laboratory in Washington decided to check the 1995 Lima report against satellite data from the same date. The satellite imagery confirmed it. There was something in the Indian Ocean that night, covering an area of approximately 15,000 square kilometers, roughly the size of Connecticut, producing enough light to be detected from space. It was not a reflection of the moon. It was not atmospheric. It was coming from the ocean surface itself. What the satellite had captured was a phenomenon that sailors had been describing for centuries and that science had been skeptical of for almost as long: the Milky Sea. The biological mechanism behind the Milky Sea is understood in outline. The light is produced by Vibrio harvae, a species of bioluminescent bacteria that, under certain conditions of water temperature, nutrient availability, and population density, can bloom to concentrations high enough that their collective light output becomes visible to the naked eye and detectable from orbit. A single Vibrio harvae bacterium produces an amount of light so small it is undetectable without sensitive instruments. But when the population density reaches approximately 100 million cells per milliliter of seawater, the combined output becomes visible. At the scale documented in the 1995 event, the total bacterial population producing the light numbered in the quintillions. This is not a metaphor. It is an estimate based on the light output per cell and the total area of the event. What is not understood is what triggers a Milky Sea event of this scale. The conditions required for Vibrio harvae to bloom to these concentrations appear to involve a specific combination of warm surface water, elevated nutrients, and calm conditions that allows the bacterial population to grow without being dispersed by mixing. But these conditions are not rare in the Indian Ocean, and Milky Sea events of the scale documented in 1995 are rare. The specific trigger, the factor that tips a population of bioluminescent bacteria from normal background concentrations to concentrations sufficient to illuminate 15,000 square kilometers of ocean surface, is not known. Satellite surveys conducted after the 2005 paper identified additional Milky Sea events in the historical record, including one in 2019 in the Indian Ocean that was tracked for approximately 45 days. This event was the first to be monitored in near real time from space, providing data on the evolution and decay of the phenomenon that no previous study had been able to obtain. The 2019 event covered a maximum area of approximately 100,000 square kilometers at its peak before gradually fading. 100,000 square kilometers of ocean surface, glowing steadily in the dark, powered by bacteria, and only visible to science because a satellite happened to be overhead. How many Milky Sea events have occurred in the parts of the ocean not covered by satellite passes with the right sensitivity and timing is unknown. The phenomenon may be far more common than the historical record suggests. The Milky Sea occupies a category of oceanic phenomenon that challenges the way we think about scale in biological systems. It is not an organism. It is not a population in the conventional sense. It is an emergent property of a bacterial community at a density that produces effects at the scale of weather systems. The boundary between biology and physics at this scale is not clear. Whether a Milky Sea event is a biological phenomenon that produces physical effects, or a physical phenomenon that exploits biological mechanisms, is a question that does not have a straightforward answer. What it is, unambiguously, is something that the ocean can do that nothing else on the planet can. An area the size of a country, producing light through pure biochemistry, visible from space, and still not fully explained after decades of study. The physics of water itself contributes to oceanic mysteries in ways that are less dramatic but more fundamental than the Milky Sea. Water is anomalous among liquids. It is one of the very few substances that is less dense as a solid than as a liquid, which is why ice floats. This property has profound consequences for life on Earth. When surface water cools in winter, it becomes denser and sinks, driving the circulation patterns that distribute heat and nutrients through the ocean. If water behaved like most liquids and became continuously denser as it approached its freezing point, ice would sink, lakes and polar seas would freeze from the bottom up, and the thermal stratification of the ocean would be fundamentally different. The anomalous density behavior of water is not incidental to the existence of life. It is one of the physical prerequisites for the ocean as a habitat. But the ocean is not simply a container of water. It is a system in which the physical properties of water interact with temperature, salinity, pressure, and biological activity in ways that produce phenomena that the properties of pure water do not predict. The thermohaline circulation, the global system of ocean currents driven by differences in water density arising from variations in temperature and salinity, moves water through all the world's ocean basins on timescales of roughly 1,000 years. A parcel of water that sinks in the North Atlantic today will resurface in the Pacific or Indian Ocean approximately 1,000 years from now. This circulation system, sometimes called the ocean conveyor belt, distributes heat from the equatorial regions toward the poles, moderates the climate of coastal regions, and transports nutrients from the deep ocean to the surface where they can support biological productivity. The circulation is not uniform. It has modes of operation, configurations of current speed and pathway that can persist for centuries and that can switch relatively rapidly from one state to another in response to changes in the freshwater input from ice melt, changes in surface temperature, or changes in wind patterns. These mode switches have occurred multiple times during the current interglacial period, and they have produced climate changes on timescales of decades that affected civilizations. The evidence for past mode switches is preserved in ice cores, in ocean sediments, and in the records of ancient climate that paleoclimatologists have been reconstructing from proxies for several decades. The evidence that the current thermohaline circulation is weakening in response to freshwater input from melting Greenland ice is a subject of active research and active scientific debate. What is not debated is that the circulation can change, that it has changed within human history, and that the consequences of a significant change would affect climate in ways that no current model can predict with confidence. The pressure gradient between the surface and the deep ocean is one of the most extreme physical gradients on Earth. At the surface, the pressure is 1 atmosphere. At the bottom of the Mariana Trench, it is approximately 1,100 atmospheres. This gradient is not simply a hostile environment for living things. It is a driver of physical processes that shape the ocean in ways that have no surface equivalent. Sound travels faster in water than in air, and faster still in cold, deep, high-pressure water. The variation in sound speed with depth produces the SOFAR channel, the sound fixing and ranging channel, a layer of minimum sound speed at depths of approximately 600 to 1,000 meters in most ocean basins. Sound waves that enter this layer from above or below are refracted back toward the layer by the speed gradient, trapped in a waveguide that allows them to propagate horizontally with very little energy loss. The SOFAR channel is the reason that underwater explosions detonated at the right depth during World War II could be detected at distances of thousands of kilometers, a property that was exploited for military purposes, and that subsequently became the basis for long-range underwater acoustic monitoring systems. The SOFAR channel is also the medium through which sounds travel that have no confirmed source. The hydrophone arrays originally deployed for submarine detection have accumulated decades of recordings in the frequency range of the SOFAR channel, and a fraction of those recordings contain sounds that have not been satisfactorily explained. The physical context matters here. The SOFAR channel is not simply a curiosity of ocean acoustics. It is a physical structure that extends across entire ocean basins, that concentrates sound energy from sources anywhere along its depth range, and that can deliver that energy to receivers thousands of kilometers away with a fidelity that allows the source to be localized by triangulation. It is, in effect, a global communication system built into the physics of the ocean, one that biology has been exploiting for as long as large marine mammals have existed, and one that science has been monitoring for a fraction of that time. The seiches, standing waves that develop in enclosed or semi-enclosed bodies of water, demonstrate how the physics of water can produce phenomena that look to the uninformed observer like something that water should not do. A seiche is an oscillation of the entire water body, set in motion by wind, atmospheric pressure changes, or seismic activity that bounces back and forth between the boundaries of the basin, with a period determined by the geometry of the basin and the depth of the water. In a large lake or fjord, seiches can raise the water level at one end by a meter or more, while lowering it at the other end by the same amount on a time scale of minutes to hours, with no obvious surface disturbance between the two ends. In coastal seas and semi-enclosed ocean basins, seiches driven by distant storms or earthquakes have produced flooding events that were initially attributed to local weather before the true cause was understood. The physics is well understood. The seiche is a solved problem, but the experience of water rising on a calm day with no weather in sight, driven by a wave oscillating across a basin too large to see from shore, connects to the broader principle that the ocean operates on spatial scales that human intuition, calibrated to the scale of human experience, is poorly equipped to interpret. The methane hydrates stored in ocean sediments represent one of the largest and least understood repositories of carbon on Earth. Methane hydrate is a form of water ice in which methane molecules are trapped within the crystal lattice of the ice, forming a solid that looks like dirty snow but burns when ignited. It forms under the conditions of high pressure and low temperature that characterize ocean sediments at depths of roughly 300 to 500 meters and below. The total amount of methane stored in seafloor hydrates is estimated to exceed the carbon content of all known conventional fossil fuel reserves, though the uncertainty on this estimate is large. The hydrates are stable under current ocean conditions, but they are sensitive to changes in temperature and pressure. If bottom water temperatures rise significantly, or if the hydrates are disturbed by slope instability or drilling, the methane can be released rapidly, rising through the water column and potentially entering the atmosphere. Methane is a potent greenhouse gas, and the possibility of a large-scale destabilization of seafloor hydrates releasing massive amounts of methane has been discussed as a potential positive feedback mechanism in climate change scenarios. The Storegga slide, a massive submarine landslide that occurred off the coast of Norway approximately 8,000 years ago and generated a tsunami that affected coastlines across the North Sea, is thought to have involved the destabilization of methane hydrates in the sediment, and the release of methane associated with it may have contributed to a brief period of warming in the climate record. The ocean floor is not static. It moves, shifts, and releases in ways that have consequences for the atmosphere above and the coastlines at its edges, and the energy stored in its sediments in the form of methane hydrates represents a potential for change that is not yet fully characterized. The internal waves that propagate through the deep ocean along the boundaries between water layers of different density are among the largest waves on Earth, yet they are invisible from the surface. An internal wave propagating along the thermocline, the boundary between warm surface water and cold deep water, can have an amplitude of 100 meters or more and a wavelength of tens of kilometers. These are waves with a vertical extent comparable to a skyscraper and a horizontal extent comparable to a city, moving through the interior of the ocean at speeds of 1 to 2 meters per second, carrying enormous amounts of energy and stirring the water column as they pass. They break on the slopes of underwater ridges and seamounts, dissipating their energy in turbulent mixing that moves heat and nutrients vertically through the water column. The role of internal waves in ocean mixing is recognized as significant, but has been difficult to quantify because the waves are invisible from satellites and difficult to measure with ship-based instruments. The total energy budget of the ocean, the accounting of where energy enters, how it is transported, and where it is dissipated, remains an open problem, partly because the contribution of internal waves to mixing is not fully measured. The ocean has a turbulent interior that is almost entirely hidden from observation, driven by processes that operate at scales ranging from millimeters to hundreds of kilometers. And the interaction of these processes with each other and with the ocean's boundaries is a problem that oceanography is still working to close. The rogue waves that mariners described for centuries and that oceanographers dismissed as exaggeration until the 1990s are now understood to be a real physical phenomenon with a frequency of occurrence that the statistical models of wave behavior did not predict. A rogue wave is defined as a wave whose height exceeds twice the significant wave height of the surrounding sea state. In open ocean conditions with a significant wave height of 5 meters, a rogue wave would be 10 meters or higher. In severe storms with significant wave heights of 15 meters, a rogue wave would exceed 30 meters. The existence of waves this large occurring far more frequently than the standard statistical models of ocean waves predicted was confirmed by data from the European Space Agency's ERS-1 and ERS-2 radar satellites in 2001. The MaxWave project analyzed 3 weeks of satellite data and identified 10 individual waves exceeding 25 meters in height in ocean conditions where the standard model predicted the probability of such a wave occurring. Anywhere on Earth during that period to be essentially 0, 10 waves, 3 weeks. The model was wrong by orders of magnitude. The physical mechanism that produces rogue waves, the process by which energy from a large number of smaller waves can concentrate into a single wave of exceptional height, involves non-linear wave interactions that the linear models of ocean wave statistics do not capture. The physics is now better understood. The waves are now monitored by satellite. But the ships that were lost to rogue waves in the decades before the phenomenon was scientifically acknowledged, ships whose sinkings were attributed to human error or mechanical failure because the wave that caused them was deemed physically impossible, represent a cost of the gap between what the ocean can do and what science believed it capable of doing. The ocean does not conform to the models built to describe it. It operates by its own physics, at its own scales, on its own schedule, and the distance between what we have measured and what we have not is still, by any honest accounting, very large. On the 19th of May, 1997, the hydrophone arrays of the United States National Oceanic and Atmospheric Administration recorded a sound in the equatorial Pacific Ocean. The sound lasted approximately 1 minute. It was detected simultaneously by sensors separated by nearly 5,000 kilometers, which meant that the sound had propagated through the SOFAR channel across a significant fraction of the Pacific Basin and still arrived with enough energy to trigger multiple sensors. The frequency of the sound was extremely low, well below the range of human hearing, which meant that no one heard it when it happened. It existed only as a trace on a recording, a shape on a spectrogram, a pattern of frequency against time that the analysts who reviewed the data found unusual enough to flag for further examination. They named it Julia. They did not know what had made it. 29 years later, they still do not know with certainty. Julia is one of several sounds in the catalog maintained by NOAA's Pacific Marine Environmental Laboratory that remain without a confirmed source explanation. The catalog exists because of the infrastructure built during the Cold War to monitor the oceans for submarine activity. The sound surveillance system, known as SOSUS, was a network of hydrophone arrays installed on the seafloor across the Atlantic and Pacific Oceans beginning in the 1950s, designed to detect the acoustic signatures of Soviet submarines at the ranges achievable through the SOFAR channel. The system worked. It detected submarines at distances of thousands of kilometers. It also detected everything else that made sound in the ocean at the right frequencies, including whale calls, underwater volcanic eruptions, iceberg groundings, and a category of sounds that did not match any of these known sources. When SOSUS data was declassified and made available to civilian researchers in the early 1990s, marine scientists gained access to decades of recordings they had never been able to make with their own equipment. What they found in those recordings was not entirely explainable. The bloop is the most widely known of the unexplained SOSUS sounds, and the one that has generated the most public attention, partly because it was given a name that is easy to remember, and partly because its characteristics are genuinely remarkable. The bloop was recorded in the summer of 1997, overlapping in time with Julia by hydrophones in the equatorial Pacific. Its frequency profile shows a rapid rise in frequency over the course of the sound, a characteristic that NOAA analysts described as consistent with the sounds produced by large biological organisms. This description, which appeared in the official summary of the recording, was not a claim that a large unknown animal had produced the sound. It was a technical observation about the frequency profile of the sound matching the general shape of biological vocalizations rather than the sustained, low-frequency profiles of geological sources like underwater earthquakes or volcanic activity. The distinction was lost in the public reporting that followed, and the bloop became famous as the sound of a possible sea monster, which it almost certainly is not. The most widely accepted explanation for the bloop among the scientists who have analyzed it is that it was produced by icequake activity, the cracking and fracturing of large ice formations in the Antarctic, a process that can produce sounds with frequency profiles broadly similar to the bloop's spectrogram. This explanation was developed primarily by Christopher Fox of NOAA's VENTS program, who noted that the location from which the bloop appeared to originate, calculated by triangulating the arrival times at multiple hydrophone stations, was consistent with Antarctic ice activity rather than open ocean. The icequake explanation is plausible and is accepted by most researchers who have examined the recording. It is not definitively confirmed. The bloop has not been reproduced, and the specific acoustic event that produced it has not been identified. The explanation is the best available fit to the data, not a proven cause. The distinction matters because the category of sounds for which no explanation, even at this level of confidence, exists, is larger than the public discussion of the bloop suggests. The upsweep is a sound that has been recorded continuously with seasonal variation in intensity since SOSA's data became available to researchers. Unlike the bloop, which was a single event, the upsweep is ongoing. It consists of a series of long, narrow-band upsweeping tones occurring throughout the year, with peaks in spring and autumn. Its source has been localized to an area of the Pacific near active submarine volcanic sites, and the leading hypothesis is that it is produced by volcanic activity, specifically by the resonance of magma chambers or hydrothermal systems, responding to tidal or pressure changes. The volcanic origin hypothesis is supported by the correlation of upsweep intensity with seismic activity in the region and by the location of the source. It is not confirmed by direct observation of any specific volcanic process producing the sound. The upsweep continues to be recorded. Its intensity has varied over the decades, declining from the levels recorded in the early 1990s, but remaining detectable. Whatever is producing it has been producing it for at least 30 years. The train is a sound recorded in March of 1997 that moves at approximately 15 kilometers per hour in a straight line across the Pacific, a speed and trajectory consistent with a large iceberg drifting with ocean currents. The iceberg hypothesis for train is more straightforwardly supported than the explanations for the Bloop or Julia, and most researchers who have analyzed it accept it as the likely cause. The whistle, recorded in July of 1997, is a brief tonal sound whose source has been localized to a seamount and is thought to be produced by water flow over the seamount's topography, analogous to the sound produced when wind passes over a bottle opening. The slowdown, recorded in May of 1994, is a sound lasting approximately 7 minutes that decreases in frequency over its duration. It has been localized to a region in the southern Pacific, and its cause is uncertain, with both geological and biological explanations having been proposed and neither confirmed. What the NOAA catalog of unexplained sounds represents is not a collection of mysteries that science has failed to solve. It is a sample of the acoustic output of the ocean, drawn from a monitoring system that covers a fraction of the total ocean volume, recorded over a period of decades that is short relative to the timescales on which the ocean operates. The sounds that have been named and discussed publicly are the ones that were unusual enough to attract attention in the analysis of SOSA's and subsequent hydrophone data. The baseline of what is normal in the deep ocean acoustic environment, what sounds the ocean makes routinely, and what signatures are genuinely anomalous, is still being established. Acoustic monitoring of the deep ocean outside the areas covered by the Cold War hydrophone arrays remains sparse. Large areas of the Indian Ocean, the Southern Ocean, and the deep Pacific are not covered by any permanent monitoring system. What sounds these regions produce and whether they contain acoustic events comparable to or exceeding those in the documented catalog is unknown. The relationship between ocean acoustics and seismic activity is one of the more productive areas of current research in understanding the deep ocean's acoustic environment. Underwater earthquakes produce sounds across a wide frequency range, from the very low frequencies that propagate through the SOFAR channel to higher frequencies that attenuate more rapidly. The acoustic signals from submarine earthquakes have been used to locate seismic events in areas without land-based seismometer coverage, extending the global seismic monitoring network into regions of the ocean floor that would otherwise be acoustically invisible. Submarine volcanoes produce acoustic signals during both eruptive and non-eruptive phases, including the hydroacoustic signals generated by lava entering the water, and the resonant signals from magma movement within volcanic conduits. The acoustic monitoring of submarine volcanic systems has produced some of the best real-time data on underwater eruption dynamics ever obtained. Because hydrophone arrays can detect the onset of eruption through acoustic precursors before the eruption is large enough to be detected by other means. The ocean is acoustically transparent to the low frequencies that propagate through the SOFAR channel in a way that the atmosphere is not. And this transparency has made hydroacoustic monitoring one of the most effective tools for observing geological processes on the seafloor from a distance. The biological component of the deep ocean's acoustic environment is itself incompletely characterized. Blue whales, fin whales, and other large baleen whales produce calls in the frequency range of the SOFAR channel, and their vocalizations propagate to distances of hundreds to thousands of kilometers under favorable conditions. The seasonal patterns of whale calling, the geographic distribution of calling populations, and the long-term trends in call frequency have all been documented through hydrophone monitoring. But the total acoustic output of the ocean's biological community, including the sounds produced by fish, crustaceans, and the vast numbers of organisms in the deep scattering layer that have never been acoustically characterized, represents a background against which anomalous sounds must be distinguished. The deep scattering layer itself produces sound. The snapping of crustacean appendages, the swim bladder resonances of mesopelagic fish, the collective acoustic output of organisms, numbering in the trillions, performing their daily vertical migration, creates a low-level biological noise that permeates the ocean at depths between 200 and 1,000 meters. This biological noise has been measured and characterized in some regions and time periods. It has not been comprehensively characterized across the full range of the ocean and all seasons. The possibility that some of the unexplained sounds in the NOAA catalog were produced by large biological organisms has not been formally ruled out. The bloop's frequency profile, whatever its actual source, does share characteristics with the vocalizations of large animals. The biological explanation was not proposed seriously as an alternative to geological sources by the scientists who analyzed the recording, partly because no known animal produces sounds of that intensity at those frequencies, and partly because the biological diversity of the deep ocean is sufficiently unknown that the absence of a known source animal is not a strong argument against a biological origin. The colossal squid, the largest known invertebrate by mass, is not known to be capable of producing sounds detectable at oceanic ranges. But the colossal squid was essentially unknown until 2007. The argument that no large unknown organism exists in the deep ocean capable of producing anomalous sounds is the same argument that was made about the giant squid for a century and a half. And the giant squid existed throughout that entire period, alive in the ocean, producing whatever sounds it produces, entirely unobserved. The acoustic tomography of the ocean, the technique of using the travel times of known sound sources to infer the temperature and density structure of the water column, has provided another window into the physical state of the ocean interior that is otherwise inaccessible to direct measurement. By transmitting precisely timed sound pulses between known locations and measuring the arrival times at receivers, researchers can calculate the average temperature of the water column along the acoustic path because sound travels faster in warmer water and slower in colder water. The acoustic thermometry of Ocean Climate Project, conducted across the Pacific between the 1990s and 2000s, used this technique to monitor basin-scale changes in ocean temperature over time. The results confirmed that the deep Pacific was warming at rates consistent with the predictions of climate models, providing independent evidence for the ocean heat uptake that is one of the primary signatures of anthropogenic climate change. The ocean's acoustic properties, a physical consequence of its temperature and salinity structure, became a monitoring tool for the state of the climate system. The ocean communicates its condition through sound to those with instruments sensitive enough to listen. The infrasound produced by ocean surface waves interacting with each other and with the seafloor creates a continuous background of very low-frequency sound known as the oceanic microsystem, detectable by seismometers on land, thousands of kilometers from the nearest coast. This signal, generated by the nonlinear interaction of ocean waves at frequencies around 1/10 of a hertz, is one of the most persistent signals in the global seismic record. Seismologists monitoring networks for earthquake signals must distinguish earthquakes from the continuous oceanic microsystem that masks signals at the frequencies it occupies. The microsystem varies in intensity with ocean wave activity, increasing during storms and decreasing during calm periods, and its geographic pattern reflects the distribution of wave activity in the world's ocean basins. The ocean is so acoustically active that its noise reaches the solid earth beneath it and propagates through the planet's crust to seismometers on every continent. The ocean is always making sound. The question has never been whether the ocean is silent. The question is what all the sound means, and whether somewhere in the frequencies we cannot hear and the recordings we have not yet analyzed, there is something in the catalog that does not fit any category science has yet built for it. The direction-finding limitations of the Cold War hydrophone arrays have shaped which sounds entered the catalog and which did not. The SOSA's arrays were optimized for detecting the acoustic signatures of submarines moving through specific ocean corridors. Their coverage was uneven, their sensitivity varied with frequency, and their ability to localize sources with precision depended on the geometry of the array relative to the source. A sound originating in a region of poor array coverage, or at a frequency outside the system's sensitivity band, or from a source moving in a way that complicated triangulation, might have been recorded without being analyzable. The catalog of unexplained sounds is therefore not a complete accounting of anomalous acoustic events in the ocean. It is a sample of the anomalous events that fell within the detection envelope of a system designed for a different purpose. The sounds outside that envelope, the ones that propagated through regions without coverage, or at frequencies the arrays were not tuned to, or during periods when the recording systems were offline, or the data was never reviewed, are not in any catalog. They happened. They propagated through the SOFAR channel to distances of thousands of kilometers, and they left no record that science has access to. The ocean has been talking since long before anyone was listening. What is said before the first hydrophone was lowered into the water is gone. What it is saying right now, in the frequencies below what humans can hear, in the ocean basins where no hydrophone array exists, in the dark water between the sensors, is not being recorded. And whatever is making those sounds, known or unknown, geological or biological, continues regardless of whether an instrument is present to receive the signal. The interaction between human-generated noise and the natural acoustic environment of the deep ocean is itself a kind of mystery in progress. The low-frequency noise from commercial shipping has increased by approximately 10 decibels across most of the world's oceans since the 1960s, roughly doubling the acoustic energy in the frequency bands that both large whales and the SOFAR channel propagate most efficiently. This noise increase has reduced the effective communication range of blue and fin whales, compressed the acoustic space available for biological signaling, and raised the background level against which any anomalous sound must be detected. A sound that would have been detectable against the pre-industrial ocean background at a range of 1,000 kilometers may only be detectable at 300 kilometers in today's noisier ocean. The anomalous sounds that entered the NOAA catalog were recorded against a background already elevated by decades of shipping. Whether comparable events occurred before the shipping era, whether they were more frequent or less frequent, whether the ocean's acoustic character before industrialization contained patterns that are now masked by noise, is unknowable from the data available. The acoustic history of the ocean before human industry began altering it is not recoverable. What the ocean sounded like when only natural sources contributed to its acoustic environment was signals moved through the SOFAR channel in the centuries before the first steamship, is a silence that no instrument recorded and no analysis can reconstruct. The sounds we have are a fraction of what the ocean has made, and the fraction we do not have is larger, older, and deeper than anything in the catalog. The ocean has been accumulating mysteries longer than our species has existed to notice them. Every anomaly in the record, every sound without a source, every formation without an explanation, every animal that turned out to be nothing like the picture science had assembled from dead fragments, points to the same underlying fact. The ocean is not a place that science has studied and found complicated. It is a place that has repeatedly demonstrated, in the most direct possible terms, that the frameworks science brings to it are inadequate. Not wrong, exactly. Inadequate. Built for a scale that the ocean exceeds in every direction. The ratio that gets cited most often in discussions of ocean exploration is the 5% figure. we have explored approximately 5% of the ocean. The other 95% remains in the specific sense that the word exploration implies unvisited, unsampled, unobserved at the resolution required to identify what is there. This ratio is not a product of indifference. It is a product of physics and engineering. The deep ocean is not simply far away. It is an environment in which the pressure increases by 1 atmosphere for every 10 meters of depth, in which temperatures hover near freezing, in which complete darkness begins at a few hundred meters and does not end, and in which the vehicles capable of operating are expensive to build, expensive to operate, and limited in the time they can spend at depth before they must return to the surface. The cumulative time that human-operated submersibles and remotely operated vehicles have spent on the seafloor below 3,000 meters across all the expeditions ever conducted is measured in weeks. The ocean has been there for 4 billion years. The discrepancy between those two timescales is not a gap that more funding and better technology will close quickly. The 5% figure is also, in an important sense, an overestimate of what is actually known. Exploration implies not just visiting a place, but understanding what is there. The ROV footage and sediment cores and water samples collected from the explored fraction of the ocean have produced an enormous body of data, but the analysis of that data is not complete, and the picture it produces is not comprehensive. Species discovered on a single expedition to a single seamount may not have been seen again. Acoustic events recorded by hydrophone arrays have been cataloged without being explained. Sonar anomalies identified in survey data have been noted without being investigated. The explored 5% is not a 5% that is known. It is a 5% that has been visited in the way that a traveler passing through a country in a sealed vehicle might claim to have visited it. The contact has been made. The understanding has not followed at the same rate. What drives the exploration of the deep ocean is not primarily scientific curiosity, though scientific curiosity has always been present. The economic and military drivers have historically been more powerful and more consistently funded. The mapping of the seafloor was accelerated by the need to lay undersea cables and pipelines. The acoustic monitoring systems that captured the unexplained sounds were built to track submarines. The ROV technology that has provided the most detailed views of the deep seafloor was developed primarily for the oil and gas industry. The scientific programs that have produced the most significant discoveries about deep-sea biology and geology have in many cases been parasitic on infrastructure built for other purposes, opportunistically accessing data collected by systems that were not designed to answer scientific questions. This is not a criticism of the science. It is an observation about the conditions under which knowledge of the deep ocean has been accumulated. The picture of the ocean that science has assembled was built largely from the byproducts of other endeavors, from the margins of systems designed for commerce and security, from the fragments that fell within the detection range of instruments pointed at other targets. The deep ocean is the last large environment on Earth that remains genuinely unknown in the sense that the word unknown had before the age of satellite imaging made every surface of the planet visible from orbit. The rainforests of the Amazon and Congo, the ice sheets of Greenland and Antarctica, the high mountain ranges of Central Asia. These are all environments that are difficult to access and poorly studied at fine scales. But their existence and general character have been known for centuries. The major rivers, mountain ranges, and coastlines of the land surface of the Earth have been mapped at resolutions sufficient for navigation since the 19th century. The equivalent mapping of the ocean floor is not complete at the 21st century. The best current global bathymetric map of the seafloor, compiled from all available ship-based sonar surveys and satellite altimetry data, has a resolution of approximately 5 kilometers. At this resolution, a feature the size of a large building is invisible. A seamount the size of a small mountain might or might not appear, depending on its shape and the density of survey coverage in the area. The ocean floor, as it is currently mapped, is a sketch. The detail that would allow it to be called a map, in the sense that any land surface is mapped, does not exist and will not exist until a survey program on a scale that has never been funded is completed. The Nippon Foundation and GEPCO Seabed 2030 project, launched in 2016, has the explicit goal of producing a complete map of the ocean floor at 100-meter resolution by the year 2030. It is the most ambitious ocean floor mapping effort ever undertaken. As of the middle of the 2020s, it has mapped approximately 30% of the ocean floor at the target resolution, up from approximately 6% when the project began. The remaining 70% represents an enormous area, and the pace of mapping required to meet the 2030 deadline requires a sustained commitment of survey vessel time and funding that has not yet been fully secured. Whether the project will achieve its goal on schedule is uncertain. What is certain is that when it does, the map it produces will reveal features on the seafloor that have never been seen, anomalies that will generate new questions, formations that will require new expeditions to investigate, and a catalog of unknowns that will be larger and more specific than the catalog that exists today. Completing the map of the ocean floor will not reduce the number of things that science does not know about the ocean. It will increase it by revealing in detail what has previously been invisible, and by making visible the questions that the current low-resolution map cannot even ask. The relationship between the ocean's unknowns and the history of what has been discovered is not a relationship of diminishing returns. It is the opposite. Every significant discovery about the deep ocean has revealed not a reduction in what remains unknown, but an expansion of the questions that need to be asked. The discovery of hydrothermal vent ecosystems did not close a question. It opened an entirely new field of biology, a new understanding of the conditions under which life can exist, and a new set of questions about the distribution and diversity of chemosynthetic ecosystems that are still being investigated 50 years later. The acoustic monitoring that captured the Bloop and Julia did not produce answers about the deep ocean's acoustic environment. It produced a catalog of anomalies and a recognition that the acoustic environment of the deep ocean was far more complex and far less understood than anyone had previously appreciated. The ROV footage of living giant squids did not resolve questions about cephalopod biology. It revealed that everything inferred from dead specimens about the animal's behavior, appearance, and ecological role needed to be reconsidered. The pattern is consistent. The closer science looks at the deep ocean, the more there is to see. The ocean has been the source of creation in the mythologies of cultures that never had contact with each other. From the Babylonian Tiamat, to the Norse primordial sea, to the waters that existed before the world in Genesis, to the oceanic origins of life and scientific understanding. The ocean appears across unconnected traditions as the place from which everything came. This convergence is not coincidence. It reflects a genuine intuition about the relationship between the ocean and existence. Life did originate in the ocean. The chemistry that makes living organisms possible, the specific molecular architectures of proteins and nucleic acids and cell membranes, were assembled in conditions that the early ocean provided, conditions that did not exist on the land surface of the early Earth. The ocean is not the symbolic origin of life. It is the actual origin of life. And the environment in which life originated, the chemistry that drove the first metabolic reactions, the physical conditions that allowed the first self-replicating molecules to form and persist, those conditions still exist in the deep ocean, in the hydrothermal vents and cold seeps and chemosynthetic communities that have been operating on the same basic chemistry for billions of years. The deep ocean is not merely a habitat. It is a record of the conditions in which life first assembled itself, preserved in the ongoing chemistry of places that have barely changed since the Archean. The particular quality of the ocean as an unknown is different from the quality of other unknowns. The interior of a distant planet is unknown in a way that implies inaccessibility, a fundamental physical barrier between the observer and the observed. The deep ocean is not inaccessible in this sense. It is here. It is on this planet, beneath a layer of water that is thick enough to create extreme physical conditions, but thin enough to be traversed by machines that human hands have built. The animals that have never been seen are separated from the surface by hundreds of meters of water, not by light years of vacuum. The structures on the seafloor that may carry evidence of prehistoric human habitation are within diving range of existing vessels. The sounds in the NOAA catalog that lack confirmed sources are recorded on instruments that any oceanographic research program can access. The ocean's unknowns are not unknowns of distance. They are unknowns of depth, which is a different kind of distance, one measured in pressure and darkness rather than space, and one that the history of exploration suggests is navigable, slowly, incompletely, one expedition at a time. The question of what the ocean means, in the sense that things can mean something to minds capable of interpretation, is not a scientific question. It is the kind of question that arises after the scientific questions have been asked and answered and found to generate more questions than they resolve. The ocean means different things in different registers. In the register of chemistry, it is a medium in which certain reactions occur. In the register of physics, it is a fluid with measurable properties responding to external forces. In the register of biology, it is a habitat containing organisms that have adapted to its conditions. In the register of geology, it is a surface feature of a tectonically active planet, temporary on geological timescales, destined to change in configuration as the plates continue to move. In the register of climate, it is the primary heat reservoir and carbon sink that moderates the atmospheric system within which all surface life operates. None of these registers is wrong. None of them is complete. The ocean is all of these things simultaneously, and the interaction between these registers, the way that chemistry drives biology, and biology modifies chemistry, and physics constrains both, and geology reshapes all of them over time, is a complexity that no single scientific framework has been built to hold. The experience of being in proximity to the ocean, of standing at its edge or floating on its surface, connects to something in human psychology that predates the scientific frameworks that have been built to understand it. The response that most people have to the open ocean, to the sight of water extending to the horizon without visible end, involves a recognizable quality of feeling that the writer Romain Rolland described in correspondence with Freud as the oceanic feeling, a sense of boundlessness, of the dissolution of the boundary between self and environment, of something vast and continuous that the ordinary categories of experience do not contain. Rolland was not writing about the ocean specifically, though the name he gave the feeling is not accidental. But the ocean is among the most reliable natural triggers for this response, and the response is not incidental to why the ocean has occupied such a central place in human culture, mythology, and imagination since the earliest evidence of symbolic thought. The deep ocean amplifies this response. An environment that extends downward for 11 kilometers, that contains ecosystems that have never been seen, that produces sounds that no human ear has ever heard, that holds structures whose origin science has not been able to determine, is not an environment that ordinary categories of experience are adequate to. It exceeds them. And in exceeding them, it produces the particular quality of feeling that attaches to genuine unknowns, not the frustration of a solvable problem that has not yet been solved, but the specific sensation of standing at the edge of something that is larger than the frameworks available to comprehend it. The structures remain on the seafloor. The animals continue in the dark. And somewhere in the part of the ocean that no instrument has yet reached, in the water column above the deepest trenches, in the sediment that covers the buried coastlines of the glacial world, in the frequency bands below the threshold of human hearing, there are things that no category science has yet built is adequate to describe. That is not a comforting thought. It is not meant to be. The ocean is not a comfortable place. It is a place where the rules that govern surface life do not apply, where the scale exceeds anything human experience prepared the brain to process, where the darkness is total, and the pressure is lethal, and the temperature is close to freezing, and life not only survives, but thrives, in forms that nothing about the surface world would lead you to predict. The part of this planet that is most alive is the part that is least known. That combination, maximum life, minimum knowledge, maximum depth, is not a coincidence. It is the ocean. It has always been the ocean. What sits behind everything described in this documentary represents centuries of effort by thousands of researchers working at the edge of what was technically possible in their time. The whalers who first described the bloop-like sounds from below the surface and were not believed. The divers who descended to Yonaguni and surfaced with accounts that qualified scientists dismissed for years. The sonar operators aboard Cold War submarines who logged acoustic anomalies in classified records that civilian science would not see for decades. The biologists who published estimates of undiscovered species that their colleagues found implausible and that subsequent expeditions consistently validated. Each of these people was working at the boundary of the known, contributing data to a picture that none of them could see in its entirety because the picture is too large and too deep and too old to be held by any single perspective. The picture that exists now is the accumulation of all of those contributions, still incomplete, still being added to, still generating more questions than answers at its edges. The boundary of the known is not a fixed line. It moves as instruments improve, and expeditions are funded, and data is analyzed, and connections are made between findings that seemed unrelated. The boundary moves outward, and behind it, always, is more ocean, more depth, more dark, more life in forms that have not been named, more sounds and frequencies that have not been recorded, more structures on the seafloor that have not been imaged. The ocean is not running out of unknowns. It is the one environment on Earth that is not. And it will remain the ocean long after every question asked about it in this moment has been answered, generating new questions in the dark, at depth, in silence that is not silence at all. If this journey moved something in you, consider subscribing to Sleep on Deep. Every week we descend a little further. The ocean is waiting.